So, welcome to this text mining webinar today. My name is Julian and I'm working as a data scientist for KNIME. I'm doing the workshop together with my colleague Andisa, who is also working as a data scientist for KNIME. And this webinar is split into two different parts. At first, I will show you how to create a named entity recognition model and a co-occurrence networks in KNIME. And afterwards, Andisa will guide you through the process of sentiment analysis using KNIME's deep learning integration. Each part will take around 40 minutes. And after each of these 40 minutes, we will have a small Q&A session where we will answer your questions. And to give us questions, there is a Q&A tool in Zoom, which you can use, and there are also some other NIMers which will answer your questions during the session, and after my session I will answer some more questions in case there are questions that the other NIMers couldn't answer right now. The session will be recorded on YouTube, and will be available on YouTube, and the link will be shared after the session on our website. So I will start with my part. As I've said, it's about named entity recognition and co-occurrence networks. At first, I will tell you something about today's use case in general. Afterwards, I will guide you through the different tasks that had to be solved. I will show you how to train an NER model and how to collect documents to do so. I show you how to extract named entities from documents and how these entities can be used to create a co-occurrence network. I will also show you how to create an interactive view in KNIME. And in the last step, I will show you how to extract specific subgraphs to get more information from your network. So at first, about the use case, our goal is to train an NER model that recognizes drug names in biomedical literature. The second goal is to create a drug-drug co-occurrence network. And afterwards, we will use this drug-drug co-occurrence network to predict the purpose of a drug. I will say something about it later in the presentation. After we create our network and predict the purpose, we also extract, visualize and validate some interesting subgraphs so that we can have a look if our prediction was correct. There aren't basically not much requirements, but having a decent document collection is very important to successfully train an NER model. So one part of this use case is to create a known document collection that can be used to train the model and to extract named entities from. As said, documents are required to train a model, but not only plain documents, but annotated documents. There are two different ways to annotate documents. One way would be the manual annotation, which is very time consuming. And another way would be the automatic annotation, which is more error prone, for example, due to ambiguity, but it's much faster. And in this workshop, we will collect documents from PubMed and use automatic annotation, since I want to show you how to easily train an NER model with low effort. To create the document collection, we first have to think about the named entities our model should detect in the end. So since we want to identify drug names in biomedical literature, we use drugs that are covered by the WHO's ATC classification system. It contains around 800 drugs and drug combinations. There are different types of drug names, like generic drug names, brand names, and chemical names, but we will only use generic drug names, since brand names make the detection a lot harder, since there are brand names like Stay Awake, which is pretty hard to detect in this context of drug names. As we can see in the table, there are several drug names and their corresponding ATC code. The ATC code is defines basically the purpose of the drug and classifies them into different groups. And the ATC code itself consists of 5 different levels. The first letter is the first level. The second 2 digits are the second level, and so on. And in this workshop, we will only need the first level of the ATC code, which stands for 1 of 14 anatomical main groups. So the letter N, for example, stands for drugs for the nervous system, and D stands for dermatologicals, and so on. In the next step, I will show you a small example. So we have acetyl salicylic acid with the ATC code NO2BA01, where N stands for the drug for nervous system, NO2 stands for analgesics and painkillers, NO2B stands for other analgesics and antipyretics, NO2BA stands for salicylic acid and derivatives, and NO2BA01 defines the actual substance name. So this is our ATC code, and we have our drug list that we got from the WHO, and we also got our ATC code, which define the purpose of the drug. Now, when we use our model later, we will also detect some new drug names in our literature where we don't know what purpose these drugs are for. And that is why we create the Co-Occurrence network and later on predict also the first level for these newly detected drugs. So back to the document collection. After defining our set of drug names, we can finally start to collect these documents. In this case, we download documents from PubMed. PubMed is an openly available search engine for biomedical literature with more than 29 million entries. And for each dictionary entry, PubMed will be queried using the document grabber node. I will show you the workflows later. But another thing, it is important that you don't use just a random set of documents, but to collect a specific set of documents that is based on the entities from the dictionary. And therefore, we will use the document grabber node. And since some drugs have many hits on PubMed, I restricted the maximum number of results per query to 100. So in the end, I have a collection of approximately 72,000 documents. So let me show you the first workflow. So the workflow is split into, the work is split into 4 different workflows. I have one workflow for the document collection, one workflow for the model training, one for the co-occurrence network, and one for the to extract the subgraphs. The first workflow basically gathers all the documents. In this first step, we parse a WHO website to get the drugs and the ATC codes. When we have a look at the table, we can see that we have 810 drugs with their specific ATC codes. We also parsed a description for these ATC codes, so we can see each level, for example, level A, AO2, and so on. And in the next step, we send this list to this meta node, to this component, where we gather these articles. We have the document grabber node in the middle and put it into a loop, and each drug name will now be queried in PubMed, and we download approximately maximum 100 documents. So that in the end we get around 75,000 documents. We get the document name and the document title and the query name, and write it to a table that then will be used in the next workflow where we train the model. So to prepare the documents for training the model, we want to ensure that there are enough sample sentences for each drug name. So we can only train a model when we have enough sample sentences so that the model knows what it has to do when it tries to detect new entities. And to do so, I removed drug names with less than 20 hits on PubMed, and also documents that did not contain the exact query term, because they only contained related words. And after filtering the documents, the reduced set of documents has approximately 45,000 unique documents. To train the NER model, we will use a StanfordNLP NE learner node, which we can see here. The learner node has two input ports. One is for the training documents, and one is for the dictionary of drug names, of our known drug names, basically. Internally, the node annotates the document based on the dictionary and creates a model, which is in this case a linear chain conditional random field, or CRF model, which is quite popular in the field of natural language processing, because it does not only classify a word based on the word itself, like many other discrete classifiers, but it can also take adjacent words into account. So before training, we will split the document collection into a training and a test set with using the partitioning node. And we are using 10% for the training set, which are around 5,000 documents, which seem to be enough for training the model in this case. When we have a look at the StanfordNLP NE learner node, we can see many different options. Since I'm only using the standard, the default settings, I only want you to show some that might be relevant. Among them are the use word, use n-grams, no mid n-grams, and maximum n-gram length options. And there's also a small example, which I will show you now. We have the word acetyl salicylic acid. If we check the option use word, the whole word will be used as a feature for our model. If we use the use n-grams option, we also get like substrings of the word as features. For example, acetyl or salicylic or acid. And we also can define the maximum n-gram length. So there won't be any feature longer than 10. Yes. If we check the no mid n-grams option, nothing will be used as a feature that is not in the beginning or the end of a word. So this small fragment of the word will not be used as a feature. However, it always depends on the use case. So in this case, since we have drug names which have like always same drug stems and names that sound similar, it's a bit easier than for other use cases, but it's still possible. So after training the model, we can evaluate the model by using the StanfordNLP NE Scorer node. The Scorer node has two input ports, one for the test documents and one for the model. The Scorer node annotates a document in two different ways. Once with using regular expressions based on our dictionary that we created in the beginning, and once by using the trained NER model. And afterwards, it basically compares both statistics. So for example, we have this little table here with some drug names like insulin, insulin aspart, and insulin isophane. And the regex-based annotation gives us a tag for insulin and insulin aspart, and the model only for insulin and insulin isophane. This shows that there might be some drawbacks with statistics like false positives and false negatives, because in this case, this regex annotation should be our baseline, which is used to compare to our model. And since insulin isophane was not tagged, but the model tagged it, we can assume that this might be an entirely new term that the model has tagged. So there might always be a small bias in these statistics in this case, but in general it looks quite well. Yes, there's another node from StanfordNLP using the StanfordNLP library, which is a StanfordNLP NE tagger. This is used to actually tag new documents with our trained model. As we can see here, we have the model, we have documents. The upper port needs the document, the optional port needs our model. There are also some default models in this node that can be used to tag names and company names and stuff like that. In this step, we want to extract the named entities from our documents. So afterwards, we use a modifiable term filter, which erases all words that are not drug names, that have not been tagged as drug names. Afterwards, we use our bag of words creator, which basically creates a set of drug names for each document, and for each drug name only occurs one time in each bag of words for each document. So in total, we have 180,000 annotations in the document collection that we had in the beginning. Among these annotations, we have 1,500 unique entities. From these entities, 730 were in our drug dictionary in the beginning, and we found 800 entirely new entities. And for example, we have insulin isophane, as we've seen, and pipendoxyphene. As you can see, the name resembles a lot the other drug names, so you could guess that this is also a drug. But we still have to validate it. So let's have a look at the workflow again. So after creating our drug collection, we have the second workflow where we read the table that we got from the first workflow. Afterwards, we prepare and filter the documents. We, as I've said, we filter documents with where the query term didn't occur, so that we have a list of documents, and we also group these documents by the query term. So some documents are used for several terms. We also have a list of our used dictionary, and this will then be fed to the Stanford NLP learner. Here we do the partitioning into the training and the test data set, where the training set will be fed to the Stanford NLP learner. Afterwards, we have two validation nodes, one to validate the training set and one to validate the test set. And here I created a view. I can only show you the validation of the training set yet, because I accidentally reset the other node, and it takes quite a while. So the interactive view shows you, wait a bit, shows you the confusion matrix from the Stanford NLP NE Scorer, and I also did some more validation. So here we have a list of false positives and false negatives. So we have the drug name, we have the number of occurrences that occurred by using the regex annotation, and we have a column that shows the number of occurrences by using our model. And it also shows you if we have false negatives or false positives. And then there's also a list of newly detected entities in the bottom. So on the bottom right part, we have also the part where we actually extract the entities by using the Stanford NLP NE tagger, the term filter, and the bag of words creator. We have in the end a list of all our annotations, a unique list of all the annotations we got. And then we also write these tables again so that we can use it in the next workflow I will show you later. So then let's come back to the slides. There's my mouse. There we are. So in the next step, we will create a co-occurrence network. To count term co-occurrences, we can use the term co-occurrence counter node, which is also part of the text mining extension. So afterwards, we will create a network where each drug name will be a node, and your co-occurring named entities will be connected by an edge. To add some more visual features to the network, we will color the nodes by using the first level of the ATC code, and we will also visualize the node shapes. And in this case, we will visualize entities from our dictionary as circles and newly detected entities as squares. In the bottom here, we can see how a term co-occurrence table looks like. So we have two term columns and one counter column. So basically, these two drugs are mentioned together in one document. To create the network, we actually use 3 or 4 nodes in this case. The first one is the network creator node, which basically just creates a data type that stores the network in the background. So in the beginning, it's just an empty network. And afterwards, we use the object inserter, which adds nodes and edges. We use the feature inserter node, which adds visual features to the network. And then we can use the JavaScript network viewer to actually view our network. So let's have a look at the node dialog of the object inserter node. As I've said, the node is used to add nodes and edges to a network. We have two important settings here. This is the node ID column and the second node ID column, where we just specify the column name of the term co-occurrence table that we got before. And when we add both of these columns, the edges between these nodes are set automatically. Then we have the feature inserter. The feature inserter is used to set visual properties to a network. And there are three important configurations. The first one is the name of the property, which then can be selected by the viewer nodes. We have the type, which defines the type of the property, if it's a color or shape. Then we have the value column, which basically is a column which stores the color information, which I will show you as well later. There's also a multi-feature inserter node, which allows you to basically insert multiple features at once, so you can add the color, the shape, without using multiple feature inserter in a line. So in the end, we have the network viewer node. It is basically just used to show the network. It provides different algorithms to lay out the network, which can be selected interactively in the view. And you can, as I've said before, set the node shape and color, and outline color, and edge thickness, and all these kinds of stuff. It is also possible to generate an image, which you can see here. This little green port shows when an image has been created. And this image can then be used to for reports or whatever you need it for. So in the end, we get a quite huge network, which consists of 1,500 nodes and 40,000, around 40,000 edges. But it's pretty big, so it's not that fun to look at it. So we want to extract some subgraphs, which I will show you later. But first, let's have a look at the network creation process and have a look at the workflow there. So there I will go to the next workflow, which is 03 co-occurrence network. Here we also read again the data from the previous workflows. We have a term co-occurrence counter. We filter some co-occurrences because we don't want to have co-occurrences from one drug to itself. And we can have a look here at the table that we've created in this component. So we have term co-occurrence table with some more information, which we added from the data below here, which is basically the first drug, the second drug, the co-occurrence counter, and where the drug came from. Was it in our first drug list, or was it detected by our model? And it also shows the first letter of our ATC code. Yes. So here we have the network creation process. We have the network creator, the object inserter. After the object inserter, we also do the ATC prediction. I don't want to go too much into detail there because it's basically just a majority vote within the network. So basically, when we have a drug name that is detected entirely new, then we look at the neighborhood within this network and label our newly detected drug with an ATC code from calculated from the neighborhood, basically. Afterwards, we set the visual properties. I can show you something here a bit. So we have the color manager node, the shape manager node, and where you can basically set colors for each nominal value here. We have a shape manager, which is basically the same. We have circles for our drugs that are contained in our dictionary and rectangles for drugs that are not contained in our dictionary. Afterwards, we have to extract these properties into a column. So it looks like this. And these values can then be used by the feature inserter node to actually insert the features to the network. In the end, I had just a random subgraph because the whole network would be a bit too big to show, but I will just open it now and also show you the interactivity feature. So this is quite big. We have many different drugs and drug names. You can now select some of these drugs and go to the bottom where is a table of all these drug names with some more information about it, like the description of the first level of the ATC code. And we can also show selected entities of the network as well. So if I click some of these nodes here, then I will only get this node and some more information about it. So yes, now we want to validate our ATC prediction. To do so, we want to extract some subgraphs of our network because right now we can't really, the network is quite big and we can't really see how the prediction worked out. And to do so, we just extract connected components of newly identified named entities and their first neighborhood of named entities. So I have a small example for this. Here on the right side, we have 4 newly detected drugs and 1 drug that was in our drug list. This is a drug which is used in cancer treatment, and all these drugs, when you look them up, they are also drugs used for cancer treatment. So the prediction in this case was working out quite well. But as you can see, the name is pretty similar, and this is a bit easier for drugs since the drug names and stems are well defined. So it always makes sense if the stems are similar. On the left side, we have also some newly detected drugs, and here it is not that clear, but all the blue colored drugs are drugs for our sexual hormones and used for like treatment in breast cancer and stuff like that. We have 2 brown ones, which are also used for breast cancer treatment. And when we look these 4 up, we can see that these are estrogen receptor modulator, which also fits quite well, and they are also used for breast cancer treatment. So it seemed to work quite well. This is it so far from my side. Now I will show you the workflow with the subgraph extraction. So here we read our network. We filter the nodes basically so that we only have our nodes that were newly detected. We get a component list with connected components. Then we extract the subgraphs from our full network and do some filtering in the end, because when we filter nodes, there might be some edges dangling around and some nodes that have no connections anymore. And in the end, there is a small view. Yes. So this is it so far from my side. One note I have. So this was basically a use case for the biomedical domain, but you can imagine this is possible for any other domain. So you can, when you don't want to train your own model, but create a network, just get some RSS feeds for a newspaper and use a StanfordNLP NE tagger, which also provides some predefined models to tag some names and locations and companies and whatever, and create your own network. But you can also try out to use the StanfordNLP NE learner. I think it's quite easy to use, and you get some good results. So this is it so far from my side. I will check the Q&A now so that I can answer some questions. So I will just have a look here. Hey James, so the NER taggers right now don't put out the confidence, unfortunately, because our text processing framework and the term structure that we are using does not allow us to add some additional information like the confidence measure, but it's on our list, so we know about this. Juan, how do you define how many samples are enough for your training data set? It depends. So yeah, it's really hard to say. So I went for like 20, but I guess the more the better. But I think the results were quite fine with at least 20 samples per QE. Sharon Peterson, what additional validation did you do? So for validation, I had the confusion matrix by the scorer. And as well, the table that I've shown before, I can show it again. So in this view, where we have like the list of false positives and negatives, so that you can see how good the quality of the model is, where all of my drug names really tagged by the model. So in this case, we can see there are some differences, which we usually don't want to have. On the other hand, when we have 0 on this side and another value on a value bigger than 0 on this side, we know that we have a newly detected entity. And furthermore, we also have, like the last step, the extraction of the subgraphs as a validation. So you can have a look at the ATC prediction if you're interested in, and then have a look at the basically at the drugs on the internet and check if it fits to the scheme of the other drugs that are connected to this drug. So where's my mouse again? Okay, Gabriel. That seems weird. It should not happen, but I can come back to you later, and we can try to fix it. At Andy, can the co-occurrence frequency be used to make bigger edges? Yes, this is possible. So in the network viewer node, we have also, let me go into this component, and here we have the node dialog for the network viewer, where we have the edge settings and the edge size feature. So in this case, you would have to create a column that will be fed to the network viewer, and then you can basically select the co-occurrence count and use it as a size feature. At Repco, can you please explain how to use other languages like English than English, like Dutch? So for the StanfordNLP NE learner node, you just can use a collection of Dutch text and Dutch words, and it should work out fine to create a model for Dutch language. There aren't many. I don't think there's any pre-installed model for Dutch language, but I'm not sure right now. But to create your own model, this should work out the same way I explained right now. So at Andy Hertzberg, where you get the workflow, so the workflow is either on the hub or on the example server with NER. I think it's when we have a look at the example server, it is under other analytic types, chemistry and life sciences, and then under prediction of drug purposes. There are the 4 workflows and the data we used. There's also a blog post regarding this topic on KNIME with the same title, basically. To Hidir, where's the deep learning part? Did I miss the part? No, you didn't miss it. It will follow after my session, where Andisa will talk about sentiment analysis with KNIME's deep learning integration. I now have to finish my presentation since I reached my limit, but I will answer the other questions that are in the Q&A by hand, and then I hopefully can satisfy you all. So thanks a lot for listening, and now I will hand over to Andisa, which will show you how to do sentiment analysis in KNIME.
Yes, thank you, Julian.
Yeah.
So hi everyone, my name is Andisa Dewi, and now I will continue with the other topic, sentiment analysis with deep learning. In this session, we will learn about what is sentiment analysis and how to transform textual data to make it suitable for deep learning model. Then we will move on to the deep learning part, where we will learn the basic definition of deep neural network. And at the end, I will show how to build a simple deep learning model for sentiment analysis. As in the previous session, if you have any questions, then please post them to the Q&A section, and I will try to answer them at the end of the session. Okay, let's get started with sentiment analysis. What is sentiment analysis? Let's start by considering the following scenario. Now, let's say that we want to buy a phone. What do we do nowadays? We will go to a shopping website, for example, Amazon, and we find a phone with the model that we want, and then we will check the reviews. And based on what's written on the reviews, usually we will decide whether to buy the phone or not. So it is very important for companies or manufacturers to analyze these reviews so they can gain insights about the overall sentiment of the customers about their product. And this is exactly the task of sentiment analysis. So sentiment analysis is basically the analysis of textual data that is trying to identify the sentiment of the text, and the easiest form usually is positive and negative. So this means it's a binary classification problem. And there are more fine-grained sentiment analysis approaches that are trying to predict different classes, such as very positive, neutral, very negative, or they're trying to predict irony or other structures. But in our case, we will keep it simple. We just have two classes, positive and negative, and that's it. And here, in this example, you see two sentences. The first sentence is clearly positive, and the second sentence is clearly negative. So this application of sentiment analysis is very useful, not only for product review for product vendors, but also if you think of a hotel reviews or Airbnb reviews or restaurant reviews, then of course for all of those hotels, vendors and restaurants, it makes sense for them to understand the opinion of their customers. Okay, to be easier defined, then sentiment analysis is a field of the natural language processing that builds a system that tries to determine an opinion, for example, positive or negative, within text. And sentiment analysis is very important in text mining because it can help to transform unstructured information into structured data of opinions about products, brands, or any other topic. It is sometimes also referred as opinion mining or emotion AI. For emotion AI, the classes could be different. For example, that could be things like happy or unhappy, but in the end, it is really similar. There are several approaches on how to do sentiment analysis. For example, the traditional approach, which is the lexicon base, where we use a dictionary that contains positive and negative words. And we classify a document based on the number of the positive and negative words that are contained in the document. Or there is the machine learning approach. For example, we use the decision tree to classify the documents. Or there is this deep learning approach where we build and train a deep learning model. And in this workshop, we will focus on this part. So in general, sentiment analysis usually follows the following philosophy. At the beginning, of course, we start with reading the data. If you use KNIME, there are a lot of different options to read the data from. For example, from CSV or from TXT files. And we can also use the TK parser node to read from PDF files or from various other sources. And then we convert them to a document format. And a document format is, if you're not yet familiar, it is a special data type in KNIME where we use to handle documents or text data. And the next step is the preprocessing step. And in this step is where we usually remove or filter out words that we don't need or that are unnecessary. And after the data is clean, we need to transform the text into numerical data. And the last step is to take these numbers to build a model for the sentiment classification. So in the following slides, I will explain each of these steps in more details and how to do them in KNIME. Now let's start with reading and parsing the data. For sentiment analysis, the data that we usually have will contain two columns. One describes the documents that we want to analyze, and the other is the label. This label determines whether the text is positive or negative. In KNIME, we can use the file reader node to import the data, for example, from CSV file. And after that, we use the strings to document node to convert the strings to document format, which we need to process textual data in KNIME. And after we imported the data, we need to clean them. And we do that by pre-processing the data. This step includes, for example, we remove the punctuations, we remove any small words, for example, any words that are less than 1 or 2 characters will be removed, and numbers as well, and any stop words. As an example, we have 3 reviews here. Let's consider the first one. So this movie is horrible, dot, the acting is a wastebasket, dot, dot, so the scenery is great, dot. By applying the pre-processing component, the sentence turned into movie, horrible, acting, wastebasket, scenery. So now you can see that the punctuations are removed, all the unnecessary stop words are gone, etc. As a side note, for this step, it is optional, so some people do this and some people don't, and we have tried both, and we found that the result, if we use the pre-processing step, is a little better than without, so we decided just to keep this step. Okay, the third step is transformation. Now, there are a lot of ways how to do it in general. For example, what we can do is we can extract all the terms in the documents, and then we calculate the term frequency, which is the number of times a term appears in one document. And at the end, we transform each document into a numerical representation, a document vector, using, for example, the term frequency values, or the one-hot encoding approach, where we just set 1 to a term if it appears in the document and 0 otherwise. So as a result, as we can see here, we have a vector where each row is one document and each column represents one term. However, for deep learning, we need to use another approach for the numerical transformation. It is because the deep learning network expects as an input not only a numerical representation of the words, but we also need to take into account the order of the words in the document. So for instance, for the document here on the left side, we need to build a dictionary where each word in the document is assigned to a unique number, or let's call it an index. And then together with the dictionary replacer nodes, it will replace each word with their corresponding number. So at the end, what you can see is that a sequence of numbers that represents this document on the left side, and it is now a numerical representation of this document, and also the order of the words is maintained. The other requirement is that the network also expects each document to have an equivalent length. So to solve this, we need to specify a maximum number of words that are allowed in each document. And for documents that are shorter than that, we will fill the gaps by padding them with zeros. And for long documents, we have to truncate them, meaning we just cut them off. We take only the first, for example, 50 words or 1,000 words, depending on your data. For example, if you're analyzing Twitter data, then you know how long it should be. Or if you have different documents or any longer documents, then you have to find out yourself how many words should be allowed in this document. For those purposes, we have created two components. One component is to truncate long documents, and one component is to pad the short documents with zeros. Okay, to make the transformation process clearer, I will give a small example in the next slide. So in this example, we use the same three reviews as we have seen before. As mentioned before, the first step is to build a dictionary where each word in all the documents is assigned to a unique number. So here we have 10 unique words. So we have 10 unique numbers in the dictionary. Then we apply the dictionary with the dictionary replacer nodes, and we get the following result. So we get 3 document factors. Now let's check the first factor. What we have is the word movie as the first word. And in a dictionary, we see that it is assigned to number 2. So in our factor, number 2, we have number 2 at the beginning. And the next word is we have horrible, and horrible is assigned to number 8. So the next number is 8, and so on like that. Now we can see that these factors, they don't have the same length yet, but we know that the network expects factors of equivalent length. So what we need to do is first, we have to set a number of words in this document. Now let's say that we want to have a maximum of 5 words per document. So we apply the truncate component, where 10 long documents will be truncated into 5 words. Now we can see that because the first document had 6 words, the last word is removed, so what's left are the first 5 words. But we still have here documents that contain less than 5 words. So we then apply the zero pad components to pad the gaps with zeros. So at the end, we get from each document a numerical factor that has the same length. And now our data is transformed and they are ready for the next step. Okay, if you look in KNIME, this pipeline describes the reading, preprocessing, and the transformation of the data. So it is exactly the same as the example that I explained before, but this is how we will do it using KNIME nodes. So first, we will read in our data with the table reader node, the upper part. And the data that we have are movie reviews. And we convert them into documents with the strings to document node. And we preprocess the documents using the preprocessing component. In addition, we also read in the dictionary with the table reader node on the lower part. In this example, we don't assign all of the words in the documents its own index because there are so many of them. So instead, what we do, we take only the first 20,000 words, which are the most frequently used, and assign them with an index. For this purpose, we have the create dictionary component where we can decide how many words that we want to keep in the dictionary. And the rest of the words are then filtered out by the dictionary filter node. Next, we truncate long documents with the truncate component, and then we apply the dictionary with the dictionary replacer nodes. And at the end, we pad zeros to the shorter documents with the zero pad component. The result that you can see on the right side is where the documents are transformed into a list or the numerical sequences of the documents. This is the overview of the whole workflow for your orientation. And so far, we have done these steps, the reading and pre-processing of the data. And the next step is the classification, where we first have to build the network topology. And then, after building the network, we will train and evaluate the model that we built based on the data. So the model that we're going to build is a deep neural network model. So before we start building it, I will give a short and simple introduction to deep neural network. And since deep neural network is based on neural network, so first I will start with a neural network, and then I will come to the deep neural network. Okay, so what is neural network? It mimics basically the biological neurons in our brain. And these neurons interact with each other, and these interactions allow us to perform activities with our body. Now, I will give you a very simple illustration, and it's really simple on how the neurons are responsible for performing tasks in our body. Now, first, let's say that you want to raise your hand. So first, what you will do is that, of course, you will think about it, right? Now, in our brains, there are billions of neurons that are connected to each other. And I have here a simple illustration of that. I have a picture of a brain, and those red circles, they represent some of those neurons. Now, this illustration is very simple, so it is in no way represent the actual structure of a brain, and it's really only for the purpose of this small example. Take it with a grain of salt. Now, when you think about raising your hand, there's a neuron somewhere in the brain that takes this thought as an input, and we call it an input neuron. And in the illustration, it is the green node. And what it does is that it takes this thought as an input, and then it forwards and processes this information to other neurons along the way until it reaches the final neuron that will make you raise your hand. And we call this the output neuron. So this whole process can be represented by the artificial neural network, as we can see here. And this network is organized in layers. Again, we have the input layer that contains input neurons. And from our example, it was the neuron that gets our thoughts. And we have the output layer that contains output neurons, like the one that is responsible to raise the hand. And in between, we have the so-called hidden layers that contain neurons that are responsible to forward and process information from the input to the output neurons. So basically, artificial neural network is a set of algorithms that is inspired by the human brain, and it is very useful in different areas, such as for pattern recognition or for classification, which is the task that we want to do in this workshop. So, and then what is a deep neural network? So it is actually simply a neural network that has a lot of hidden layers. And those hidden layers, they have various functionalities, such as convolutional, embedding, recurrence, etc. Now let's get back and see the network that we want to build. We have 4 layers, the input layer, the embedding layer, the LSTM layer, and the dense layer. And this is the simplified version of our network topology. Again, we have 4 layers, the input layer, and then we have 2 hidden layers, the embedding layer and the LSTM layer. And at the end, we have our output layer, which is the dense layer. And in the next slides, I will explain each of the layer in more details. So we start with the input layer. The input layer takes input data from the outside world and passes them into the network. In our use case, our input data are documents. Now let's go back to our previous example. So here, back then, we have 3 numerical factors where each factor represents 1 document. So remember here that we have chosen 5 words as the length for all documents. So this means that the dimension for the input layer, or the number of neurons in this layer, is 5. Each neuron is responsible for 1 word. And in general, the dimension of the input layer for our use case is n, which is the number of words in its document. And the next layer is the embedding layer. The idea of the word embedding is that we embed each word into a dense high-dimensional vector. And why do we do this? It's because similarities and relationships between words can be found in high-dimensional space where similar vectors are grouped together in the vector space. So what this layer does is it produces vector space where word vectors that share common context are located near each other in the space. And there is a famous example of this if you do the calculation between the word for the vector for the word king minus the word man plus the word woman, it would be equal to the vector of the word queen, which makes sense semantically. And that's why capturing such relationships could provide a performance boost in our sentiment analysis tests. Now back to our use case. As input, we have the output from the input layer, which is a vector of size n, where n is the number of words for its document. And after applying the embedding layer, the output of this layer will be n times m dimension, where we have n words in its document, and each word is represented by a vector of size m. Now the next layer is the LSTM layer. But before I start with LSTM, I will give a very brief introduction to the recurrent neural network, or RNN, because the LSTM is a type of RNN. I will not go into the mathematical background behind this, but basically the difference between RNN and neural network is that in RNN, after calculating the output in one step, the result is then fed back as additional information in the next step, where the next data is calculated, and so on. So it is, you can say it is similar to a loop where in each iteration, it will take into consideration all information from previous iterations, and this enables RNN to memorize history. And that's why RNN is suitable to analyze sequential data, where the order of the data is very important. For example, like text or time series. However, RNN, the drawback is that RNN is unreliable for handling long-term memory. So if we have a lot of data, then RNN will have to memorize all of the history, which makes it harder for the network to train. And this is caused by the so-called vanishing or exploding gradient problem. And that's why LSTM, or the long short-term memory, is developed. It is a variant of RNN where it can handle long-term memory. improvement is that LSTM has the so-called gates that allows it to forget old or unnecessary history, and leaving only the relevant information behind. And this concept keeps the model really simple and easier to train. For the dimension in LSTM, remember that the output from the embedding layer is a matrix of dimension n times m, which is the representation of one document. And this will be the input for LSTM. And then it will be aggregated into one vector of dimension p for each document. And the last layer is the output layer, which is the dense layer. This layer is very straightforward because what it does is just connects each unit of input with each output unit. And at this point, our input is a vector of size p. And for our sentiment analysis, we want our output to be a number that indicates whether this document is positive or negative. So what we need is a function that maps this vector to one value. And this function is called an activation function. We use sigmoid as the activation function, and therefore we'll get result. We'll get as the result is a value between 0 and 1. And we can then define a boundary. Let's say values that are larger than 0.5 will mean that the document is positive, and then if it's less, it is negative. Okay, so until now we have the basic idea of what each of the layer in our network does, and later at the demo at the end, and I will show as well the node dialog of each of these layers in KNIME. One thing to note as well is that all of these layers, this pipeline with the embedding layer and the LSTM layer and the dense layer, they are the commonly used deep learning pipeline for sentiment analysis. But however, it is not the only way to do it. So you can also try out using different layers. You can add more layers or remove some. It's really all depending on your needs or your data. Now in KNIME, we have the Keras integration that allows us to build our own deep learning model without having to write a single line of code. And there are a lot of different type of layers with over, I think around 60 nodes. And besides building your own model, you can also, for example, train your own network from scratch. You can execute already trained networks. You can also read any pre-trained Keras networks for transfer learning. And if you prefer to write code, then KNIME also has a Python deep learning integration where you can use it together with the Keras integration. For example, if you want to edit an already trained networks, or if you're already familiar with Python, then you can also write your own networks. And another thing is that if you prefer to use TensorFlow, then there is also the TensorFlow integration that allows you to convert, for example, a Keras network into a TensorFlow model. So in this workshop, then we will use these following 4-layer nodes. Now back to the workflow, we have learned how to define the network, and now we have to train the model using the Keras network learner node with part of the input data. And in order to check if the model is good, of course, we have to evaluate it using the other part of the data. And here we partition the data into the training and test sets. And then after the model is trained, we apply the model on the test data for predictions using the Keras network executor node. So at the end, we use the scorer node to show the classification result. Now to train the network, we use the Keras network learner node. And in the node dialog, there are a lot of parameters that you can tune. But for the concept of our workshop, we will build only a simple model using the default parameter values. However, there are some interesting parameters that you might want to change. Here at the top is the backend. We use TensorFlow library as the backend for Keras, but of course, if you use others like CNTK, for example, then you can change the backend here. And there is also the epoch. And epoch is the number of times that you allow the model to see the complete training set. Of course, you have to experiment a bit here to find the optimal epoch for your data. And you also have to be careful because the more epoch that you set, then the more times you will allow the model to see the complete data, then it might overfit. And if it is too less, it might underfit the data. The next is the training batch, which means that how many documents that you want to train in each iteration. And then there's also the optimizer, which is the function that the model uses to minimize the error at each iteration. After executing the learner nodes, you can right-click on the node and open the interactive view of the learning monitor. And it shows the training progress in real time. You can see the line chart of the accuracy and loss as the training progresses, also the current epochs and the current batch size. On the right side, it shows as well the current accuracy value. And at the lower part of the window, there is a stop learning button that you can use if, for example, if you're already satisfied with the current accuracy, then you can simply stop the learning anytime. The data set that we are using is, as I mentioned before, they are movie reviews, and it is a subset of the IMDb movie reviews. It contains 50,000 documents with their associated sentiment labels. And they are evenly divided between positive and negative reviews. And the goal here is to assign the correct sentiment label for each document. To set up the Keras integration in KNIME, what you need to do is first you need to install the Keras integration extension. And to do that is very simple. Just go to the file and click the install KNIME extensions, and then you can search for the extensions there via the search box and install it. And the most important thing is that because Keras relies on Python, of course, you also need to set up Python for deep learning using Anaconda. And also set up the environments with the Keras and TensorFlow. If you want to use GPU, you can also do it. Then you can simply install the Keras GPU package, for example. I will not go into the installation details here, but if you want to know more about it, the step-by-step, which version of the packages to install and other things, then you can check the Keras installation guide that I provide in the link below here. Okay, and this I also collected some references for more information. Basically, if you want to learn more about the word embedding layer, what's the background behind it, how it happens, then we have a blog post that explains everything in more detail. And there is also, if you want to know more about RNN or the LSTM, we also have another blog post that explains everything really in details. And if you want to learn more about the Keras integration in KNIME or about the TensorFlow integrations, then you can also go to the links I provided here and to check out all the informations that are available. Okay, I think that's it from the slides. Now I will show you a little bit of the demo. I will go to the workflow and show you some of the notes. Yes, so this is our workflow. I think the preprocessing part is already clear enough, so I will not explain it again. And we can see the network here, and we start with the input layer. Of course, if you remember, then the shape is basically the dimension of the input data, and it is the maximum number of words that we allow in each document. And in this example, we set the maximum number of words for each of the review to be 80. So we set this to 80. And in the embedding layer, this input dimension is the size of the dictionary that we have. In our case, it is 20,000. And here I have 20,000 plus 1, and 1 is the 0 index. It is a special, and it is reserved for the padding. And that's why the 0 is not included in the dictionary itself. So we need to include this here. That's why we have the 20,001. And the output dimension, this is, if you remember in the slide, it was our M dimension. And this is basically the size of the factor size of each of the word. And in our case, we want to here to 128. Of course, you can set it to other value depending on your data. You can, I think around 100 is also okay. But basically, you just need to try out different values to see which is good for your data. And in the LSTM layer, here, this units is also, it describes the dimensionality of the output unit. So here I also set it to 128. From our example before, this was our P size factor, so the output of the LSTM layer. And here I also set it to 128. And the rest of the parameters, I just use the default one. And in the last layers is the dense layer. And of course, the units is the output size of the factor, because we only want to have one value for our prediction. Then we set this to 1. And we set this activation function to sigmoid, which will return values between 0 and 1. Now we see our Keras network learner. So here there are 3 tabs that are important. So we have this input data, we have the target data, and the options. And in the input data, because our input data is a sequence of numbers, so we, in the conversion, we select from collection of numbers, and we input here our input sequence. And in the target data, of course, we want at the end to have one number. So we say here from number, and we give here the target or the sentiment column in our data. And here you can also select the loss function. And since in our example it is a binary classification, we can set, it is okay to use the binary cross entropy. You can select any other, and there is also, if you want, you can write your own custom loss functions using Python. And in the option tab, yeah, it is the same that I have explained in the slides before. And this learner node, it has 3 input ports, and the first port is the model port for the network. So here you connect it to the last layer of your network topology. And the second layer is your training data. So we connect this to the training set or the training part of the partition data. And the third one is the optional. It is an optional port that you can use if you want to have a validation set. And in our network executor, there is basically similar to the trainer. You have this input, where we also input this our input sequence, and we have also our output data here. And it has two input ports. The first, of course, we connect it to the output or to the model from the network learner. And the second port is for the taste data. So it's to the lower part of the partition data. The result of this executor node, if you can see here, I'll try to increase, okay, is that it will give values between 0 and 1, as I mentioned before, and since it's not clear, we cannot compare it yet with our actual label class, so we need an extra rule engine node so that we can say, for example, for all the values that are larger than 0.5, then we set it to 1, and if it's less, then we set it to 0. So here you can see that now we have our prediction column, which contains values between 0 and 1, and we can use now the scorer nodes to compare between these two columns. And we can see the result in the confusion matrix, where the overall accuracy is around 79.82%. And this is good. This is pretty good. And since we are using only the default parameters, there is a lot of room for improvement. So you can do more parameter tuning. You can try out different values for different parameters, and you can see if the accuracy will improve. Yeah, I think, okay, that's it for this session. And now I will check the Q&A section to see if there are any questions. Okay, there is a question from zero padding ensures that all vectors will have the same length, but this means that the neurons that mostly get the value 0 will be inactive most of the time. So what you mean here that if we do zero padding, then we'll have a lot of zeros in the vectors. It really depends on what the value that you set as the maximum number of words that you allow in this document. So for example, let's say if you have Twitter data, then of course it doesn't make sense if you set the maximum number of words to be like 500, because the maximum is only around 200 something. So it really depends on your data. So if you have mostly short documents, then you can set it to, I don't know, the average length of the documents. And if you have longer, then you can set it to longer. So it really depends on your data, and you have to analyze it to get the optimal maximum number of words in this document. And the second question, it is possible in KNIME to define a loop that computes the base result for different models, and then select the best model. Okay, so so it is like the parameter optimization, or yes, of course we have. You can do that. In this case, I can show you a little bit. So there is this we have this loop nodes, which is called the parameter optimization loop. And I think this is not part of the default KNIME installation. You can, I think it's called, you have to install an additional extension, and it's called, I think, the optimization extension. So with this, what you can do is that, for example, if you want to do parameter tuning, let's say you want to play around with the, let's say with the dropout parameter in the LSTM layer. So you can open this node dialog, and then you can add a new parameter, and you set the start value and the stop value of this parameter, and also the step size. The step size means that in each iteration, the value will be increased by this much step size. You can add more parameters if you want, and you can also select your search strategy for the grid search. You can use brute force, but of course it takes a lot of computation memory, or you can select another one. And you basically what you do is that you just connect this flow variable connection to the LSTM layer. And here you go to the flow variables tab, and you search for the dropout here, for example, and then you can select the flow variable that you created in this node dialog. And at the end, of course, you need this the loop end, which you can connect to the scorer nodes, I think, or maybe the scorer. So there is also the scorer nodes. So you can connect it. Oh no, you also need, no, I think you can just directly here like this, and then you can select the accuracy, the overall accuracy. Okay, I have to execute the nodes first, but basically you can select then the overall accuracy, and then you can make it so that it calculates, or it gives the or the maximum accuracy of each of the iteration during the grid search process. And of course, beside the grid search, you can also do cross-validation. And you can even combine it as well with the parameter optimization loop. Here we have these two nodes, which you can use for cross-validation. So you can give the number of folds that you want to do, and also the sampling type, and then you can just connect this to the network learner and the other part to the executor, and then it will aggregate at the end the accuracy for each of the iteration or each of the fold. Yeah, okay. So I hope that answers the question. And the next one, is possible to use the custom weights or words of effect in embedding layer. Unfortunately, I think right now it is still not possible if you want to initialize layers using any pre-trained weights or pre-trained embedding. But what you could do is maybe you can manually create your own network, for example, using the DL Python network creator, and then you can create your own network manually with the pre-trained embedding, and then you can append it to the rest of the layers. Or for word2vec, there is another library. There is another deep learning library in KNIME, which is called, I think, DL4. Yeah, there is a library beside Keras that's called the Deep Learning for J, and here we have the word embedding section where there is the word where it contains the word-to-fact learner. So if you really want to use the word-to-fact, you can, for example, use this node, and here, with this node you can train your own word-to-fact model. And at the end, there are other nodes that you can use to extract. For example, there is this vocabulary extractor where you can use this to extract all the words in the documents and also their corresponding embedded factors. And it's really interesting because then you can, for example, you can calculate the distance between all of these vector pairs, and you can use scatter plots, and you can see the vector space where really the words with similar meaning, they will be grouped together in near each other. Yeah. If you want to know more about this, as I mentioned before, there is this links that I provide in the references and word embedding blog post. The word-to-fact will be explained in more details. So yeah, if you want to know more, then you can check that out. I think we run out. We are running late right now, so I will I will follow up on all of the other questions so that we don't have to stay here for too long. Yeah, so I think that's it for now. So again, thank you everyone for joining and for participating and for asking so many questions. Yeah, I think I will end this webinar right now then. Thank you again.